Hi everyone, today we're going to look at an example of a Rankine cycle. But before we start, I'd like to just give you a quick review of a Rankine cycle. It's usually a 4-step cycle, and from state 1 to 2, the working fluid will go through a pump, and it is usually isentropic. If you already know what it is, you can just skip ahead, but if you don't, we can do this review together. So from 2 to 3, the working fluid will go through a boiler, and it's usually isobaric, so delta P is 0. And from 3 to 4, the working fluid will go through a turbine. If it's ideal, which is not very often, delta S is 0, but most of the time it's just not ideal. So from step 4 to 1, the working fluid will go through a condenser, and that's when it's isobaric again. So now if we take a look at this example, I hope this will make more sense to you. So a Rankine cycle runs between two pressures, 5 kilopascal and 10 megapascal, with a maximum temperature of 750 K. The quality of the fluid at state 1 is, so I'm going to start listing all the state information. So state 1, the quality is 0, so it is a fluid. At state 2, we don't know, and state 3, X is equal to 1, and at state 4, X is equal to 0.92. And like what we usually do is to list our assumptions. So we're going to assume that the pump is isentropic. Actually, we already mentioned here, but we're going to say that anyway. So the pump is isentropic, and the boiler and the condenser, they are isobaric, and it's a simple compressible substance, and also steady flow. Also, we're going to ignore the change in kinetic energy and the change in potential energy. So now we're good with the setup of the problem. And we're asked to find the isentropic efficiency of the turbine and the thermal efficiency of the cycle. Let's start with the thermal efficiency of the cycle. So if you recall, the thermal efficiency is equal to the work, the net work, over the heat input. And the work is coming from the pump and the turbine. So basically that means it's work from 1 to 2 plus work from 3 to 4 over the only heat input in this case is just the boiler here. A lot of people are confused about this because this is the only thing that we pay for. So we're going to put Q23 in the denominator. And from our steady flow energy equation, we know that m dot over H2 minus H1 is equal to negative W from 1 to 2. Same thing for W, the work from 3 to 4. So H4 minus H3 is equal to negative work from 3 to 4. Similarly, for the heat from 2 to 3, it's H3 minus H2 is equal to Q2 to 3. Okay? So now if we just plug in all these equations into our thermal efficiency, all the m's will cancel out. So we're left with H1 minus H2 Be careful since there's a negative sign in front of the word, so I flipped the sign of H1 and H2. So that's why it's a H1 minus H2 instead of H2 minus H1 here. So same thing, so it's going to be H3 minus H4 over H3 minus H2. So now we simplify this problem from calculating a lot of stuff into just finding all the H's. So H1, 2, 3, and 4. If we can find all these values, then we're good with the thermal efficiency, right? So now let's start with the fun part, finding H's. So let's look at state 1 first. So we know at state 1, let me choose a color. So at state 1, we know that P1 is 5 kilopascal. And X is equal to 0. So if we go to the saturation table, find P is equal to 5 kilopascal and temperature not the temperature, the H1 should equal to the H at liquid state, which is 136.435 kilojoule per kg. Okay, so we already found one of them. At the same time, we're also going to find the S1 at this state, because this will help us to find information that we need for state 2. Okay, so S1 is equal to SF, which is the liquid state of entropy, which is 0.4716 kilogram per kg, kilojoule per kilogram per kilojoule per kg K. Yeah, this is what I was going to say. Okay, so now we're good with state 1. Now moving on to state 2. I'm going to move my state 2 a little above here. Okay, so for state 2, we know that P2 is 10 megapascal. And it's also an isentropic pump. So if we look at the, originally we said that from state 1 to 2, it's an isentropic process. So that means S2 is equal to S1 is equal to 0.4716 kilojoule per kg K. And from this value, we can find H2 is equal to 146.93 kilojoule per kg. So this one, you need to look at liquid table. So now we found our second H right here. Now moving on to state 3. We know from 2 to 3 is isobaric. So that means P3 is equal to P2. That is 10 megapascal as well. And also we know the quality is equal to 1. That means it's in the vapor phase. So this one is very easy. It's H3 is just Hg at 10 megapascal. And that is 2725.5 kilojoule per kg. So we found the third one, guys. Oh, and by the way, this is also from the saturation table. So whenever you are on the state points, so x equals 1 and x equals 0, that's when you look at the saturation table, because that's still inside of the vapor dome, or on the vapor dome, actually. All right, let's get the last one, state 4. So at state 4, we know from 4 to 1, it's also isobaric. So P4 should equal to P1, which is 5 kilopascal. And we also know the quality is 0.92. So then H4 is just 0.92 times Hg plus 1 minus 0.92 times Hf. And that is 0.92 times 25601 plus 1 minus 0.92 times 136.435. And that gives us our last value, 2366.2 kilojoule per kg. All right, now we have all the H's that we need. We just need to plug in H1, H2, where's H2? Right here. H2 and H3 and H4. Plug them all back in here, and then we'll get that thermal efficiency is 0.14. Right? And if you want to visualize this on a TS diagram, it's going to be something like this. So S and T. So we start with the low pressure, so somewhere here, and the quality is equal to 0. That's why it's on the left-hand side of the dome. So this is state 1, and we're going to increase the temperature, and then goes up. It should be a straight line, and this is state 2. So from 1 to 2, we're going to increase the temperature and also increase the pressure. And then we're going to continue increase the temperature through the boiler till state 3 when the quality is equal to 1. So this is 0.3. And after the boiler, we're going to go through the turbine. So ideally, it should go straight down, but usually it's not ideal. So that's why it's going to go a little bit to the right. And then, so this will be our step 4. So this is why it's very close to 1, but it's not at 1. So it's, in this case, it's 0.92. And then goes back to state 1, close this cycle. So just to give you a quick intro for the next video. So we also want to find the isentropic efficiency. That's when we assume it will just go straight down, which is the 4S. All right, so first low pressure, and then through the pump we increase the temperature, and then go through the boiler, we increase the temperature all the way till when it's a vapor, and then we use the turbine to extract the work, and then also lower the pressure, and then goes back to its original state through a condenser. So this is a Rankine cycle example. In the next video, we're going to talk about how to find the isentropic efficiency of the turbine. So hopefully you find this video helpful. Let me know if you have any questions. Thank you.